I'm just going to do it's going to be reasonably quick. I'm just going to run through where we are with estimation, and by estimation I mean how we take our sensors and mash the data together to come up with an estimate of where the vehicle is, what its attitude is, what the wind speed is, all the other sorts of things that we want to know from the data. We have low quality sensors, they're cheap, but what we try to do with our platforms is to get enough sensors and use a bit of mathematics to get a useful and reliable solution. So some of the items which we're looking at in the next 12 months in estimation, one recurring theme has been that magnetometers, particularly as the platforms get larger, are a real hassle for setups. Because doing a compass dance with a 250 racing quad, it's vaguely amusing and you can do it pretty quickly. It takes 30 seconds to do a compass dance for a small quad. By the time you get to something like that, that's going to be really entertaining. For that. So, I mean, these are the sorts of things that we want to reduce the dependency on magnetometer operation. We've got some great stuff happening now with co-computing, some of the stuff that's available with NVIDIA boards and other things like with doing SLAM and some of these other vision technologies. So we want to be able to take that data from these vision algorithms and incorporate those into the navigation solution. And then finally, there's the issue that we've talked about a number of times, and that is how do we actually make our sensors more stable over a range of temperatures so that somebody can set their copter up inside an office environment, take it out to a work site where it's minus 10 degrees or where it's plus 45 degrees, turn it on and it doesn't come up and fail its pre-flight checks because everything's drifted and it's all the offsets are out. So they're the sorts of problems which have been, which we're aware of. I mean, there are others as well. There's improving some of the precision aspects inside the code for RTK GPS, but that's more of a code-wide level than it is an estimation issue. And then, if I've got time at the end, you know that EK3 has gone into upstream, and I'm just going to give you a very quick rundown. EK3, what's different to EKF2, and I'll just quickly cover that. So, magnetometer-free operation. Now, I've said that for copters and rovers because planes actually had magnetometer-free operation for quite some time. Yep. Because the good thing about planes is that when you take off, you take off down the runway or you fly them off the bungee, you normally do it nose first. If you don't do it nose first, misaligning your EKF is usually a secondary problem. So planes have had that ability to be able to take off, align the EKF using the GPS velocity, get to a certain speed, meets the airspeed and velocity criteria, and off they go. Works reasonably well.
Except for the takeoff in hover that we did yesterday.
Yeah, then you're under control with copter. I'm sorry, you've got to obey copter rules.
You got real control there.
If you disable all the compasses and rovers, it will go off the GPS. It just doesn't know which direction it's starting. It assumes north.
But so we could do something with rovers. If you promise not to reverse, go into reverse gear. You have to promise. Then we could lock you out of reverse gear, and then you could take it off the.
Well, you've only got choices too.
What?
But you've got a choice of two directions with reverse. Come on.
Yeah.
It actually sets the fly forward flag in rover when you're going forward, and it unsets it when you're going in reverse.
Okay, well we could.
So it actually already works on rover.
We could use the plane function. Okay, so it works at rover too. Okay, so rovers have already got it. Yeah, it's good to hear.
Except we do want to do it with fancy GPS.
Boats.
Fancy GPS. We're going to talk about that.
Okay.
Yeah, fancy GPS.
And boats and problematic.
And boats. Yeah, boats are problematic.
Not RTK.
Okay, so, and really the issue here is not that the EKF actually needs a yaw measurement from a compass while it's flying, and these are going to be completely stationary, because as soon as it starts to move around a bit, a little movement with turbulence and so on, it starts to respond, then just the correlation between the GPS velocity changes and position changes and the measurements from the IMU means it's actually able to estimate its heading, provided there's some movement. and change in velocity. So what we're talking about here is an alignment or an initialization problem. It's not really an in-flight issue. Now, and the problem we have with copters is that if you get past about anything more than about 45 degrees heading misalignment, and it'll take off, and then you get this inconsistency, you get toilet bowling, you get flyaways. The ECAF will eventually sort itself out, but it's no point but you're into the trees by the time that's happened, or you've gone 50 metres away and it's hit the fail-safe and it's gone into land mode over the water. What just happened to users in the past. So what we're looking for is, okay, how can we get the initial alignment? And there are a few options there, and probably the simplest thing, the thing that we could put in, tomorrow, is add a parameter for the user to set, and we could add maybe a Mavlink message, and have at the ground station be able to say, okay, this is my initial heading for the vehicle, and if somebody's operating up in the Arctic or somewhere where they can't use a magnetic compass, or in an environment where there's a steelworks and there's big, huge iron, steel structures around, they might just decide, I'm going to turn the compass off, I'm going to align the vehicle with true north or some other landmark or something they can use, and then they can just set the heading. And that's a pretty simple thing to put in. And actually for a lot of users that would, professional operators who actually have an understanding of what north, south, east, west is, that's an option. For consumers, that's, a lot of people aren't even aware where north is. They know vaguely the sun rises in the east, and it sort of stops about there. So it's not the solution for everybody. The other option, and also sometimes you're in an environment where you just don't have landmarks or things. You might have a magnetic compass, but maybe the magnetic compass doesn't work. We could use dual RTK GPS units and take the yaw angle from those. And if you've got a platform with enough base length between antennas, you can get to about 15 degrees accuracy pretty easily with a reasonable sized copter on a platform this size. You get to about 3 degrees accuracy on heading, if you have one on the nose and one on the tail. And the other option, and this is getting into something which is more, and the third option there is using an algorithm to very rapidly estimate the yaw angle, a dedicated algorithm to very rapidly estimate the yaw angle as soon as the copter starts to move. And that's something we could use for a consumer application where you can't afford to put an expensive GPS in. The user has no idea where north is, and a bit of movement on startup is, and it's really there just to solve the flyaway problem. And it's a user base that has lower expectations in many cases in terms of how the thing's going to fly on takeoff. So they're the options for magnetometer-free operation.
I've got a question about the dual GPS.
Yes.
You say dual RTK. I know that's the ultimate solution, but if we were to use dual traditional GPSs and put them 1.5 meters apart, could you eventually derive it from that?
No, well, they're too... Look, I've seen identical GPS units, because manufacturing tolerances and so on, produce positions that are 3 metres away from each other.
And what about from the velocities?
No, but they can't do it from the velocity. So, well, okay, I'm talking about aligning on the ground, right? Yeah. So you've got to look at the relative position. That's what we're talking about here. But the third option there is about using the velocities in the air, and the IMU data to work out what the heading is. But if you want to just work out what the heading is before you take off using the GPS position, then you really need, for our size platforms, you pretty much need something that can get down to centimetre level accuracy to be useful. Yeah, I mean, it's... Okay, the next item, and this is one that's been in the pipeline for some time, is I know we've got some work in the community looking at ways of taking camera data, image processing to do SLAM, variants on SLAM, and it's at a stage now where we really need to start getting that data into the main navigation system for the vehicle. And there are a few things that need to sort out. I mean, I think the way to do that is that we do have existing Mavlink messages which are compatible with off-board position systems. For another project, I've actually used the vision position estimate message on Mavlink, and that's already been demonstrated using a Vicon, indoor camera system and taking that data and fusing that into the ECAD. And that works okay. That message also provides not just position but also attitude of the vehicle, roll, pitch and yaw. Why they didn't use a quaternion, I don't know. I mean, it's a bit crazy that they did that. That's going to cause problems with tail sitters and things. I think we should push back up and actually push to have the Mavlink message changed for that. And then the third item to think about there with this use of these off-board systems is the issue with time stamping of the data, having a common clock. And the ECAF's able to handle up to about 200 milliseconds of latency on data and compensate for it, provided it knows what the latency is. And the problem is companion computer, SDN32 for main flight computer, running on different clocks. We need a method of synchronising, we need to get the clocks probably, it all depends on if the off-board computer's got its own IMU. If the off-board computer's got its own IMU and can do the motion compensation, then we don't need to be as accurate. But if the off-board computer doesn't have an IMU and we're having to do motion compensation using the gyros on the Pixhawk, then we need data we need the clocks to be accurate to within a millisecond of each other. Okay. Now, how do we do that over Mavlink? I don't know.
Do we have to use Mavlink? Couldn't we use the high-speed timer inputs?
Well, we could, yeah, but the thing is we don't have an interface or a standard for that yet.
We do. We have UAV cam time synchronization.
Yeah.
Yeah, but so a companion computer's going to have UAV cam?
Many of them do. TX1 does.
Some do.
Some do.
Or a simple GPIO on the one.
Yeah, GPIO.
Yeah. So that's a good idea because we could have that time.
The pulse for the
Yeah.
GPS. Yep.
Yep. Yeah. So that's the method which I used at my last job. Is we used to have this sort of PPS pulse running around the system. Funny thing was, it was TTL, and everybody thought that was going to be the easiest interface. It was the one that electrically caused them the most problems because they started running it over longer distances, and it was an unbalanced signal, and they had problems with noise pickup and things like that. So it should have been a really easy thing, but.
ArduPilot already supports that, basically, the camera hot shoot trigger.
Yeah.
Right. Okay. Oh, good.
The hardware is there.
Yeah.
Catch up, guys.
Yes. So all right. So that's external vision and attitude. I mean, we can certainly prototype straight away with the vision position estimate message, and for the position, it's not so much an issue. If it's a position in earth frame, then the timing corrections aren't as important. As soon as we end up with attitude data, we need a little bit more tightness in terms of timing, and if we're going to start sending vision estimates across in body frame and doing the motion compensation on the Pixhawk, that's when we start needing that millisecond timing accuracy. The third item, and this is one, I think we've talked about this at each ArduPilot conference. So I've been doing some work in the last few months doing thermal calibration and compensation algorithms for another project. And actually I was using a PixRacer as a sort of guinea pig for doing this. And essentially, customer agreed to buy me a bar fridge, and so I could put the drone in the bar fridge and cold soak it, and then turn it on, warm it up to a range of temperatures, and then look at the variation, and then look at the curve fits that we can do for that. It was quite amusing walking into an electrical shop with a drone saying, "I need a fridge the smallest fridge you've got that will fit this." The lady says she'll remember my face for a long time to come. I'll show you the...
Do the beers fit as well?
They did, yeah, but unfortunately I couldn't get the customer to pay for the beers. They said that I'd have to pay for the beers, but they pay for the fridge.
So it's cold loading. You can't run a fridge empty. That's wrong.
So give me some ice cream.
All right, so I'll go up to the top here. All right, so this is a Pix Racer, and this is IMU1, going from just under, what have we got up here? Just under 10 degrees. It started around about 8 degrees on the board, all the way through to about 55 degrees. Now, if you're wondering why it gets really noisy towards the end, I was having trouble getting it to go the last 10 degrees, so I got my heat gun out and started pointing it at the board.
You just let the heat up. Just
Yeah, and then it wasn't.
No, but you sat it on the bench.
I just set it on the bench,
Okay.
and you've got to be very careful. Do it in a dry environment. If it's a humid environment, you do that. But there's a good chance the condensation build up on a non-conformally coated board could be interesting. Yeah.
Why does it get extremely quiet around 20 C?
That was the logging. That was the logging system. Started throwing.
Just less samples there?
Yeah, less samples there. Yeah, we had dropouts on the logging.
Okay.
Yeah. I don't know. There was a lot of other logs on that SD card, so. Yeah. Anyway, the important thing is that sort of variations we talk about, on that particular board, we're seeing around about 1 degree per second of gyro bias drift, which is not too bad. I wasn't able to take it up. Obviously, I didn't have the capabilities to take it all the way down to -18, for somebody like Rob Lefebvre, who's crazy enough to fly in the snow. Although Randy flies in the snow. Yeah. So maybe he can do some testing for us.
Just on those bias drifts up at the high temperatures with the heat gun when you're heating it up, like just the reason for the amount of noise in the bias
because the Pix Racer's on an isolation mount, right?
So it's the vibration.
And I've got this two of them flow from the heat gun sort of blowing
So
past
it's mechanical.
It's just mechanical vibration. Yeah.
Oh, I've got a large chest freezer if you want to. You just literally sit the current in it and go down to -18 or something.
Yeah.
Do that sort of test.
That cools the beers down quicker too.
So does a CO2 fire extinguisher. Okay, so that's and you can see the characteristics with the gyros. That's the IMU2. That had around about the same. Now that gets worse as you go to lower temperatures, and then I'm told anecdotally, I've seen evidence that when they get past about 70 degrees, it starts to kick up again, and yeah.
So sorry. So what was the it was 1 degree per second? You said in drift over how many degrees? 20 degrees.
Over about 20 degrees. Yeah, about 1 degree per second over 20 degrees of temperature. Now, see, this is a sample of one, and we know from with the Pixhawks, with customer support in terms of user support in terms of logs, that about 1 in 100 or 1 in 50 Pixhawks will be the unfortunate person that's got one that's got 2 or 3 degrees per second of drift over 20 degrees, and fortunately they have 2 IMUs, and we can tell them to turn one IMU off and just use the other, and so on. But
those characteristics remain constant over the life of the sensor?
all I can say is they're consistent over a period of a few months, which is the time that we've been sort of tracking this data. I've been doing work with the other contract I'm working on. We've got a batch of boards which were tested, 100 boards that were tested 6 months ago, and then they were retested again. And there's evidence that when they were brand new off the manufacturing process, there was still some internal stresses and so on associated with the soldering and whatnot, and they've relieved. So actually, there was the variation in bias with temperatures a little bit bumpy initially, and then after a few months, they actually the unevenness has sort of gone away, and then you get a more consistent thing. And I think that was just the manufacturing process.
So older Pixhawks are likely to be better.
Yeah, aged. Yeah. Okay.
Like the devs.
Now what have we got here? These are the accelerometers. We've got some interesting characteristics here in accelerometers. Now we're seeing on accelerometers sort of around about 0.5, 0.6 meters per second squared, which is 5% of the G variation in acceleration, and that's enough. If that happens in the opposite directions for two of your accelerometers, that will cause it to fail pre-flight checks, the consistency checks, and you have to do an Excel count. And that's probably one of the biggest inconveniences, particularly with a larger platform. What do you do when it comes up and tells you you've got inconsistent accelerometers and you've got a 30 kilogram airframe that needs to be put on 6 sides for a calibration out in the middle of the field? So now the good news is that all of the IMU data, and we've done this is for a PixRacer. I've also looked at the traditional PixHawk and the PixHawk 2, and they've all follow these. You can fit all of them with a third order polynomial, just like a cubic. Provides a pretty good fit. And then I went on to look at the barrow. Now the barrow is an interesting one, and we all know anecdotally that you put it in the air, put it in out, hold, and then it drifts up and down throughout the flight 2-3 meters. And when I did the test on the barrow, now I've got some big jumps there, and I wasn't very happy about this because I've now put a sign on my workshop that says "Test in process. Do not open door unless you call this phone number." Which is my phone number. It's in our home office. I have an evaporative cooling system in the rest of the house which pumps air in from outside. It pressurises the house. And then somebody came into my office while my test was running. I was having lunch, and there was this big drop, and there were these big dips in pressure at different points in time because I left the door open. So, yeah, I mean, this is the problem. Barrow is probably the hardest sensor to do a thermal calibration with, because as soon as you go, if you have a chamber where you're blowing air in or blowing air out, it's going to vary. If it's in a house and you've got wind, or in a building and you've got wind loading on the building can pressurise, or otherwise, I don't know how practical that is, yes.
So the barrow, like the MS5611, I presume, it actually produces two 24-bit numbers, right, D1 and D2, and then it goes through its own internal lookup tables, and those have discontinuities in them. And there's two things with that. One is I'm not completely sure that the maths that we're using to go from those D1 and D2s to the estimated pressure is actually correct, because there's a whole lot of stuff in the datasheet about double precision, single precision stuff in there. And I found that there's a very similar sense of the same manufacturer for the airspeed, and I took across the maths and found that it wasn't correct, because in that datasheet they had example inputs, example outputs, and it didn't match. We need to go back to the MS5611 and make sure that that maths is actually correct. And it depends on the precise part number. The maths is different for each of the sub-part numbers. So the second thing, it might actually be worthwhile training yours on the raw D1, D2. Basically, because otherwise you've got two fits. You've got their fit from the factory, which is what populates that 8 table. Then you're doing a fit on top of that. The two are competing with each other. And I suspect you might be better, because all they're doing is a 3-step linear fit, right? With 3 stages. And this is going to be, which is going to introduce, and I've seen, and all the barrows I've tested, which is the 5611 barrows, have all had that characteristic S curve to it. That's 20-degree C point. Which requires a 5th order polynomial to fit. I suspect it'll be a lot better if you just go straight from the D1, D2 or sensor data to get the internal table.
You need to redo the test anyway.
You didn't have beer in the fridge.
That's right.
So that's thermal calibration. So now with PixHawk 2, if you own a refrigerator that can fit a board, a PixHawk 2 in, and you have a PixHawk 2 which has a heater, it's a smaller fridge. You could sell the fridge a PixHawk 2.
We are actually looking at a Peltier for the top for people would fly in Arizona and places like that.
Okay. Yeah. Coyotes are good. Yeah. Where's I going with this? Yeah. So we've got an IMU heater. So now we've got the ingredients. Not to necessarily do barrows a bit hard to get that stable pressure environment, but we have the ingredients now to cold soak a board, turn it on, and then have it automatically just linearly ramp the temperature up over a linear range. We can have a linear set point raising temperature, so we don't have all our samples in one part of the temperature range, so it's all distributed. The algorithms to actually do the curve fitting exist. We have an iterative solution that's available, open source. We also have an off-board Python-based calibrator which calculates all the coefficients, which is available open source. That needs to be modified to produce the parameters that we require for ArduPilot. And I think that you can make an argument for should it be an off-board calibration using like a Python script or something, or should it be on-board? And I don't think that either is, there isn't a right answer for everybody. I think that for developers or people that are just doing one-offs who want to visually inspect the data and make sure it's sensible and somebody didn't come in and open the office door, or they didn't get bump the table, someone didn't pick it up to have a look at it, look for something on your desk. That having the ability to be able to log the data and then visually inspect it and do the curve fit and so on, I think that's a necessary thing. On the other hand, if you want to calibrate a bunch of those and maybe, let's say Pixel 2 factory decides they're going to offer a Pixel 2 a calibration certificate and environmental testing to users that are prepared to pay more for something that's got that's had that additional, steps applied to it. Then they want something where it comes off in the factory, it goes into the thermal chamber, it gets power applied to it, and then it automatically self-calibrates itself and then saves the coefficients and provides a light or something indicator that it's successfully completed. So on-board and off-board are both required. The algorithms, there's C code and there's Python code that exists that does that. I think, but one of the cumbersome things is actually the parameter storage is something we probably need to have. It's the bit that I don't know how we're going to do that, because we have to store, for each IMU, you have to store, where you've got four polynomials, you need to store the minimum temperature for the calibration, the maximum temperature, a reference temperature, and the coefficients for each of the four polynomial coefficients. And you need to do that for each axis on each IMU.
Yeah.
So it's parameter storage.
How much data is that?
So it's about 60 floats if I did the math.
10. It's about 20, 40 bytes per axis. No, not 40 bytes per axis, because you don't need the temperature actually. So you've got 20, you've got 12 bytes for the reference temperature and min-max temperature, and then you've got 4 coefficients, which is 16 bytes times 3. So 16 times 3, plus your. So maybe it's not a huge lot of data, but
so we could store that up where we store the parameters. We've talked about this before in the bootloader, changing it so that we reserve part of our flash for permanent memory, even through bootloader through
It's a few hundred. It's like 300k. It's about 300 bytes worth of data.
Yeah, that's doable.
If it's something that you never need to edit ever again, it can go into the same place as your GCal data in the OTP.
The OTP is very limited.
No, we can use part of the storage, and it makes it generic, not just STM32, making it on Linux, etc. I'm already doing this for the radio IDs, for doing like binding IDs. So yeah, it's...
Oh, and you can put your ephemerals in there as well if you wanted to.
Yeah, that's right. We've got some reserve space, I think probably just about enough.
Yeah. Now the onboard calibrator doesn't need to store all the calibration data and then do the calibration it can operate on the data iteratively. So you've just got to store, for a fifth order calibration, you have to store a 10 by 10 matrix during the calibration procedure. So it's not, the storage requirements for the algorithm are quite reasonable. And the other thing is, you could start this up, if you're doing the calibration, you wouldn't start the EKF, for example, you wouldn't start a bunch of stuff, because it's a calibration mode.
That's only 400 bytes. That's
Yeah.
no problem at all.
So when we're actually using this data later to do the conversation, does that increase like RAM usage as such?
200 bytes.
Yeah, it does. It does increase RAM usage. And then you have to look at where you apply the calibration, and you know, you apply it in the driver layer.
Would imagine we could keep it down to 100 hertz. Right.
Okay, well this is.
flying.
Oh, look, you don't have to check you don't have to do the calibration calculation at the data rate. You can do the calibration calculation at 10 hertz.
Yes.
You could actually, in fact, you could even have.
Check the temperature change.
Yeah.
Only when it's changed by more than a degree.
Yeah.
So the
That
flag
would end up
rotates
having to be per sensor. I mean, with sensors, a temperature sensor in pretty much every IMU, and the boards do heat up differently in different.
That's right.
parts
It's
of
got to be done, and that's why it makes sense to do it in the driver.
1 degree might be too much. Make it little steps,
Yes.
little tiny twitches. So 10th of a degree or something like that might make more sense.
Or you just smooth it in over the next 5 seconds.
Yep.
That
Or just
makes-
do it at a regular interval.
Yeah.
yeah, all sorts of options.
Anyway, so, and that's one of the things where we don't, the maths is all known, isn't it? It's just one of those things, but to be useful, it needs to be something that, it's no good just having the algorithm in place. You've got to have something, it's the whole workflow. We need to think about the workflow for the user. How does the user verify that the calibration's been successful? How do we derive feedback and all those sorts of things? So getting the maths in, doing that sort of stuff, that's part of the problem, but it also requires a bit of stuff from the ground station or user interface side of things. And there's obviously documentation needs to be updated, and we need to work with the hardware manufacturers as well to make sure that we're not pushing something out that's not supported. So
One of the things we discussed a while ago on that one was when you've got your system that potentially would actually use the I/O in a loopback of some sort to say, hey, I'm in calibration mode, so that it was really easy for someone to. I like the idea of, okay, we can do it in the factory, that's cool, but I like the idea that this can be a professional level calibration for any user that wants it. The idea of just powering that up with a 5-volt source, sticking it in your fridge, or putting it in your fridge, cooling it down, then powering it up with the appropriate jumper done, and just letting it do its thing.
yeah, that's a good thing. And the difference is obviously if you sell a board that's had it done, then it would have been verified in the factory. You would have done the calibration and then repeated it and then actually verified the results and so on, and that would have been done. Yes.
So if you do a fit over a narrower temperature range, and then your operating temperature range is outside of that, how well will it extrapolate?
You don't. Well, on the other project, I didn't extrapolate because then you start having to make a decision about how far you extrapolate.
Yep.
And what do you do with the gradient? And also some of the when you do a polynomial fit outside of that, you're going to get to a fifth or a third order polynomial. You can actually get some pretty rapid changes in gradient outside
just
the data.
flatline it?
Just flatline it, yeah. Right. Now, we need to provide an indication that the board is operating outside its calibration range.
Which might need another couple of variables that use minimum max temperature or something.
Yeah, well, I think I'd already included that in the budget.
Yeah.
And that's the parameter. You've got to have a min and a max, and then you've got to have a reference temperature, which is the temperature that your calibration is centered around.
Yeah.
A simpler version without the fridge would be from ambient temperature up to 60, because you could just use the heater.
Yeah.
It wouldn't need a fridge at all.
You don't. Yeah.
But the good thing is about this, because it's a board level calibration. If you're able to set a parameter pre-start, so you get the board, you power it up, plug it into the USB, set calibrate gyro, baro, or Excel, or whatever you decide to calibrate on the next startup. You might set minimum and maximum temperature range for it or so on. Power the thing down, cold soak it, take it out into your warm, dry environment, dry air environment, apply power and walk away. And then have something light indication that when the calibration completes, it flashes either a green light to say, oh, it's good, I completed successfully, or an amber light, which is I'm doing it, or a red light as in something's failed. And then we need something along. Yeah, yeah.
So I think the procedure, you take it out of the fridge along with the 6-pack. By the time you finish the 6-pack, the calibration is done.
Exactly right.
Good to fly.
And I think that should go in the instruction manual.
Critical step.
All right, how are we going for time?
We're a little low,
That's right. That's right.
Beer two.
Are we low?
but you know,
Because I can just take a very quickly here, EKF versus EKF, EKF3 versus EKF2. What's the difference?
Backwards.
In summary,
Yes.
EK, oh, it is backwards, yes. Let me fix that now.
It's just seeing if we're awake.
Yeah, that's right. Yeah, I was just testing it. Yeah. Okay, there we go. So EKF3 estimates all three components of accelerometer bias. EKF2 just does Z. And you saw there the variation of bias with temperature, and that was one of the things, once a growing awareness that bias was affecting steady state, hover attitude, in attitude modes. And the other one is, but the problem is when you add states, you have to take states away, because practically we're limited to about 24 states for it to, 24 variables to estimate for it to work in a reasonable amount of time. So we took away the gyro scale factors, which is a bit of a downer, but the problem with the scale factors, they take a long time to learn. You've got to do quite a bit of manoeuvring to do it. And usually with copters, by the time you've learned the scale factors, which do seem to vary with temperature, unfortunately, then the flight's over and then you switch it off, and then you've got to do the whole thing over again. So we gave those away. There was something else that we've given away, but we've also picked up, and that's the third item. EKF3 estimates the quaternions or the attitudes directly. EKF2 estimates the error in the quaternions, and then corrects, and then estimates the error, and then updates the attitude using the error. It's the difference between, am I estimating the error or am I estimating the attitude, right? Now, the advantage with EKF2 is that you can start with the thing upside down, as in no initial information about its initial orientation at all, and eventually it'll just self-right itself. It's almost like as a cat, it always lands on its feet. Take a bit, but it gets there, and it gets there reliably. So if you have really bad IMU data, or your gyro's AOS or something like that happens, and it gets pulled away from its attitude position, it'll get itself back again. The downside of that mathematics, which I wasn't aware at the time, and it's something which John and I spent a lot of time seeing if we could work our way around, and we had to move on to other things, was that if you spin very rapidly around the Z-axis, it can actually develop a bit of a wobble in roll and pitch, and eventually the EKF will go red, and you'll get an EKF failure showing if you do very rapid continuous yaw spins. But if you stop spinning, it recovers. Okay. That's the downside of EKF2. So what we did with EKF3 is we said, well, okay, let's estimate the quaternions directly to get around that limitation. But what we give up then is the ability to, if you were to lose, drop IMU data out, or have an IMU data error or something that put the thing at 15 degrees out of angle, EKF3 takes longer to recover from those sort of large IMU errors.
Can you define longer?
The difference between like 15 seconds and a couple of minutes. right? It's a difference between. So this is the thing. It's normally gyro data doesn't get affected by vibration too badly, but sometimes it does, and when it does, it's really ugly. And what I've seen is that when it's affected really badly, I used to think, well, this is great, we'll be able to self-recover. But I've come to the realisation that with copters, by the time, even 15 seconds of having the attitude out, a copter's usually in the ground by then. Now with planes, in theory, it's a bit different because they fly higher and they're further up and so on, and a plane is able to, could potentially
Falls
rise
back
out.
to DCM automatically if EKF's unhealthy.
That's right, and you've got the DCM thing there, you can fall back and you've got a bit of an attitude solution and they can use the DCM get back and thing and so on.
So why can't we just do the same thing with copter?
Like the DCM? It's possible, I guess.
For short term.
For attitude.
And
For
we could
attitude,
even lower gains potentially for a short bit or something.
It doesn't actually matter because it's just that angle. We're just holding an angle. The records are still working for.
Now in practice, have a look at all the logs that have been analysed and the failures and so on that have been reported. Actually, loss of attitude due to bad IMU data isn't something that we get on copters. Usually when we get bad IMU data, it's due to clipping on accelerometers. It's the vibration affects the accelerometers. We get clipping. The thing shoots up into the air because it thinks it's dropping, but the attitude solution hangs in there. It's been a while since we've had the EKF on a copter basically just lose the attitude solution so badly it can't be flown in stabilised mode.
It could be something like a copter hits a branch, big whack, and then flies away. Yeah, it's an impulse. And the other thing is, which I found out, so if you fly into something, and you get that big shock through the inertial system and it saturates the IMU momentarily, that's also when it can be upset. Yeah.
Oh wait, it's true. We haven't seen those.
I
haven't seen
No,
any.
well, usually the copter's destroyed anyway.
Oh,
so it's a theoretical.
I've been meaning to get back to my hard-mounted PIX racer in a thing, so we'll have a test.
You're that torturer of EKFs.
Yeah. I haven't had time to have fun for a while, but we'll get back to that and we'll see how we run.
So that's where it's at. So the motivator there was to have something that would provide a more accurate solution for the majority of users, but there's a flip side to it. As always, it's a compromise. So what I'm doing at the moment is we put both out there in the master. We've got a good fly, find out what the feedback is. It'd be great to be able to restructure the EKF to actually be able to pick your maths on startup and have a lot of common stuff. Because most of the stuff between the two EKFs is common. All the logic, the fail-safe logic, the mode switching, all of that's common between them. It's really just the derivation and those sort of calculations that are different. So that's where it's at. They're both there.
If they've got different failure scenarios and we've got different IMUs with different data, is there a value in having one of each on each of your IMUs?
Well, that's what I'm flying on that copter there. I'm flying EK. Well, I can't do 4 EKFs at once, so I'm flying EKF. I've been experimenting with EKF 3 on IMU1 and EKF 2 on IMU2. But the problem is then I'm running
different data.
But why don't you run EKF? You can run them both on the same IMU. EKF2 on IMU1 and EKF3 on IMU1.
Yes, you can do that as well. Yeah. Okay, but there's so much choice.
That would give you a more direct comparison.
That's right. Look, I've done that with the two different. I've also been doing testing up here today. That's what I've been doing up in Canberra. Back in Melbourne, I've been flying them with identical IMU data and comparing them. So I've been trying to look at combinations. Anyway, this is in development code at the moment. It's in master. They both provide equivalent results. It's only when you get to the edge, those edge cases, where the behaviour and performance starts to differ.
So you're saying you need more logs of in-air collisions, so we need to all
Yes.
get out there today.
Well, actually, I was hoping we would have got some. I was hoping we would have got some last night.
in terms of mid-air collisions.
We tried. I had Solo chasing Randy all through the other planes, and we missed.
Just on the first item there, we have done successful flights of aircraft without doing any accelerometer calibration. In other words, setting 0 accel cal, turning off the accel cal warning, and flying vehicles successfully without ever having done accel cal.
Yeah.
Which is a huge step forward for consumer vehicles.
Yeah.
So if you combine the accelerometer bias calculation with a temperature measurement, can you do an approximate curve, or do you need to do your bias calibration?
Well, so this is the interesting thing. At the end of flight, but the problem is you could, in theory, build up a history of data and update points in memory, as in, okay, well, I did a flight and I was at this towards the end of flight, because you have to estimate that towards the end of flight, my biases were X, Y, and Z, and they were at temperature T.
Or just take a maximum temperature through the flight. Like, you know, we're talking people sitting on the ground tend to get a really high temperature in the sun, and they start flying, it tends to drop.
Yeah, but no, but the problem is the accelerometer bias requires you to be manoeuvring to estimate.
So you actually need a settled bias while in flight, and then at one temperature, and a settled bias while in flight, and another temperature.
Yeah, well, that's right. Yeah, so then that's the problem. You know, you need, because when you're hovering, you can't distinguish between a roll error and a bias error in your y-axis.
Yeah. Yeah.
So anyway, that's it in terms of thoughts for estimation for this year. I guess people have been asking questions as we've gone along. So, is there anything else? Okay.
That's fantastic. So thank you very much, Paul.